Okay, so welcome to this Chemistry World webinar, Powerful Technology Through Tiny Particles, Innovation with Aqueous Colloidal Silica. I'm Philip Broadwith, Chemistry World's business editor. For those of you not familiar with the GoToWebinar platform, GoToWebinar is an interactive platform. You can ask questions from our speakers at any point during the webinar. That's one of the crucial things that we think is an important part of these webinars, getting access to the experts. There's a box near the bottom of the GoToWebinar panel. By default, that's on the right-hand side of your screen. If you type any questions you have into that at any time, please do that during the course of the webinar. Don't wait until the end, especially in this case because we have a special guest to Ali, who's going to be here answering questions during the webinar. So if you miss any part of the presentation, or you want to watch it again in your own time to pick up the details or the links or anything that we're sending out, we're going to be sending a link to the recording in a few days' time. And just as a little thank you to everyone who's attended the webinar live, we will also send you a certificate of attendance in that same email. So today's webinar is about aqueous colloidal silica, which is essentially tiny particles of sand suspended in water. But as we'll hear, its properties and uses defy the simplicity of that description. Its chemical reactivity and high surface area mean colloidal silica finds applications in a host of different sectors, for example, catalysis, ceramics, and high temperature insulators. We have worked with WR Grace to bring you some information in this webinar that we think you'll be interested in from some real experts in the field. Later on, we'll be joined for the live Q&A session by Ali Kalaji, who you can see on your screen at the moment. He is a senior R&D scientist in the Materials Technology Division at Grace, and he has a wealth of experience in inorganic material synthesis and characterization, ranging in applications from LEDs to catalysts and beyond. He is going to be on hand throughout the webinar to answer your questions in the chat. So do get your questions in. As soon as you think of them, just drop them in the chat to give him the best opportunity of getting through as many of those as possible before we get to the live Q&A session at the end. But today's main presentation comes from Dave Chapman. He is a research fellow at Grace, and over his career, he has experience working with many different types of inorganic materials in a wide variety of commercial applications. Today, he's going to run through some of the properties of colloidal silica and some examples of how it can be used, some relatively conventional, some a little bit more surprising. Unfortunately, Dave can't be with us live today, so we have pre-recorded his presentation. We'll play that out in just a moment, but before we do, it's time for a quick poll. This is just a chance for us to get to know you, the audience, a little bit better. So Chris has just opened the poll for me now. So the poll today is, how familiar are you with Ludox colloidal silica? You can select one of these answers: not at all familiar, somewhat familiar, or very familiar. So I'll just leave that open for a little while to allow you guys to have a chance to vote. And as I say, once we get into the video presentation, do drop your questions into the chat as soon as you can, and we will come on to those towards the end. Okay, I can see quite a few of you voting. We'll just leave that open for a few more seconds. Yeah, I think we're coming towards a fair consensus there now. So I think, Chris, I think you can probably stop the poll now. Are we going to show the results? So it looks like, there's a lot of you here who are not at all familiar with Ludox colloidal silica. That's probably good. You're going to learn quite a lot here. Some of you who are somewhat familiar, so you'll get to top up that knowledge. And some of you who are familiar, maybe you'll see a few things that perhaps you didn't already know about the family as well. Okay, so thanks very much for that. We will now be just going to start the video. That will just take a couple of seconds to load up, and I'll hand you over to Dave Chapman.
Thank you and greetings, everyone. We'd like to share with you today some of our excitement about the ongoing technological impact of a material that has been around for a long time, and that is aqueous colloidal silica. The goals of the presentation are to provide a basic understanding of the colloid chemistry of silica, and then to highlight some interesting applications and the silica functionalities that enable the novel properties of those applications to be obtained. We'll start out by giving a bit of a historical perspective on the discovery of colloidal silica and the evolution of the Ludox colloidal silica brand. Next, we will discuss some of the basic chemical considerations, such as how the particles are typically made and stabilized, and some modifications that are commonly found in commercial products. Although there are a vast number of different applications, we will take a closer look at just 3 of these. The first involves the use of colloidal silica as a binder for other inorganic oxides, and we will use precision investment casting as an example of that application. Other similar applications as binder include catalysts and refractory fibers. Next, we will highlight how silica nanoparticles modify an organic material when dispersed in the solid matrix, with a focus on the mechanical properties of the mixture. The organic phase in this case is a thermoplastic polyurethane. Finally, we will discuss a new application wherein colloidal silica is used to modify the viscoelastic properties of an aqueous hydrogel phase. In this case, the gel mixture offers unique properties to improve the delivery and efficacy of traditional fire retardants. An early example of the preparation of colloidal silica in controlled conditions was in the laboratory of Thomas Graham almost 160 years ago. Graham noticed that a silica species of very low diffusivity was made by the partial neutralization of sodium silicate. Over 50 years later, a patent was issued for the preparation of colloidal silica by an electrodialysis method. These early colloidal sols were very dilute, however, as they were quite unstable and very reactive. A breakthrough of great technological importance occurred at Nalco when it was discovered that the colloidal sols could be prepared by a process that involved first removing the sodium ions from the silicate using ion exchange resins to make dilute silicic acid, and then silica particles could be formed and stabilized by the readdition of controlled amounts of sodium ions along with adjustment to high sol pH. These sols were stable enough to be concentrated by evaporation to nearly 30% silica. The technology was licensed to DuPont in the 1940s, and Bechtold and Snyder of DuPont subsequently patented a process to grow the colloidal particles to any size while concentrating them. This involved using small particles as seed in a heel and adding additional silicate while heating the mixture. Ludox colloidal silica was first commercialized by DuPont in 1948. In the following decades, there was extensive research and development work done in the central R&D laboratories of DuPont, and the first large-scale production facility for Ludox colloidal silica was completed in 1969 in East Chicago, Indiana. In 2000, DuPont sold the business to W.R. Grace, and in 2020, a new Ludox colloidal silica plant was completed in Worms, Germany. Colloidal silica consists of nanoscale particles of amorphous silica dispersed in a fluid phase. It is possible to synthesize particles with monomodal size distribution, but it is also possible to intentionally produce polymodal grades. This is done by inducing one or more cycles of nucleation and growth on a parent sol, which is used as seed. Alternatively, mixtures of particles of different sizes can be prepared. TEM micrographs that represent both monomodal and polymodal grades are shown here. Ludox colloidal silicas are used in an increasingly wide range of applications. Among other things, the particles can be used to modify surface properties, as binders, as coagulants, and as raw materials for specialized zeolite syntheses, along with many other. There has been very active industrial interest in colloidal silica since the first sols were commercialized. One of the first patents for Ludox colloidal silica was as a binder in a catalyst application. And of course, the binder application is still of high commercial relevance today. The graph shows the number of patent applications per year that cite Ludox colloidal silica. The steep rise in patents beginning in the early 1990s roughly corresponds to the key insight that incorporation of inorganic nanoparticles into polymer matrices can lead to improvement in the tensile properties of the polymers. Since 1948 and through August of 2020, there have been over 35,000 patent applications representing over 8,000 patent families that cite Ludox. In the next couple of slides, we present a very brief introduction to present-day colloidal silica manufacture. The key raw material is concentrated sodium silicate. The sodium ions are removed by ion exchange using acidic ion exchange resins. This creates very reactive species that are represented here as silicic acid, where the silicon nucleus is surrounded in tetrahedral coordination by 4 hydroxyl groups termed silanols. The silanols undergo condensation reactions with adjacent groups to form growing silica clusters. Once these species form nuclei, deposition of additional silicic acid causes the nascent particles to grow. The sol is then concentrated either by evaporation or ultrafiltration. Post-modification of the sols can include ion exchange of the ions in the solution phase and surface modification by inorganic or organic additives. Interestingly, the particle nucleation and growth can be modeled using classical nucleation theory. In this context, a key parameter is the solubility of silicic acid, and we can define 3 regions. At very high concentration, that is, for supersaturated solutions above the critical concentration for nucleation, nuclei can form and grow. Below this critical concentration for nucleation, but above the solubility limit, particle growth occurs without additional nucleation. Finally, the particle growth largely stops when the silicic acid concentration is below the equilibrium solubility limit. Reactor conditions that are important during particle nucleation and growth include the temperature and pH, as these strongly affect the critical and saturation concentrations. Process parameters such as the addition rate of silicate, mixing speed, and the particle size of any seed present are also important. The lower curve shows a typical reaction profile, wherein silicic acid is continuously added at a constant rate to a heel of water. The concentration builds and becomes supersaturated until the critical concentration for nucleation is surpassed. Particles then form and grow, and the deposition of silicic acid on existing particles lowers the concentration in the system to a regime where only particle growth occurs. As a result of careful process control, the particle size of the resulting sol can be controlled to have narrow-sized dispersion. Shown in the graph is a comparison of Ludox colloidal silica to some other commercially available sols. For this graph, a disk centrifuge method was used to provide an accurate representation of the particle size distribution. Another means of determining particle size distribution is by transmission electron micrograph analysis, coupled with image analysis of many TEM fields of view. The results on the right represent this approach for determining the size distribution of a different Ludox grade. In order to best understand the differences between types of colloidal silica products, as well as to gain insights into performance characteristics, it is necessary to understand some basic concepts about the nature of the particle surface. In aqueous suspensions, inorganic oxides typically develop a surface charge. A very useful model for describing the interface between the particle surface and the bulk solution is the DVLO model. In this model, an electrical double layer exists, wherein a first layer of ions is strongly bound to the particle, and the next layer of counterbalancing ions is more loosely held. Both of these 2 layers, called the double layer, are associated with the particle strongly enough that they move with it in suspension. The potential decays exponentially away from the particle surface, and the rate of decay depends on properties such as the ionic strength of the solution. A shear or slipping plane develops between the double layer and the surrounding fluid. Thus, when we measure particle charge, we are actually measuring the charge at the edge of the double layer, and this potential is called the zeta potential. This theory of the electrostatic structure of the colloidal particle surface has been successfully used for many years to describe the behavior of colloidal suspensions. The electrostatic force described previously is represented on an energy diagram as the curve in blue. This curve shows the magnitude and sign of the potential energy between two particles as a function of the distance between them. Since like charges repel each other, this repulsive energy increases as the particles approach one another. In addition to the electrostatic force, there's also a chemical force between the particles, the so-called van der Waals force. Unlike the electrostatic force, the van der Waals force is attractive, as shown in the red curve. If the electrostatic barrier can be overcome and the particles come close enough, the particles will bond together to form larger aggregates. These can precipitate out of the suspension if they are large enough. In a stable colloidal system, these two forces are nicely balanced, giving rise to a potential energy curve as shown in green. The actual shapes of the curve shown above depend on several parameters, such as the suspension pH, the electrolyte charge, the valence of the ions in solution, and other factors like specific absorption of molecules and ions, especially polymers, onto the surface. Hydrogen bonding polymers, like polyvinyl alcohol, can interact with the surface hydroxyls via hydrogen bonds. We will now describe in more detail the chemical nature of the colloidal silica surface. It consists of silanol groups and siloxane bonds. The silanols demonstrate different types of coordination. Adjacent silanols from separate silica nuclei are termed vicinal silanols. Two silanols per silicon nucleus are termed geminal silanols, and those that are separated are termed isolated. These are all somewhat acidic, so that in aqueous medium, they can deprotonate to an extent that depends on the pH. At high pH, the reaction shown is driven to the right, and the surface develops a negative charge, and so the particle has negative electrostatic character. At low pH, the reaction is driven back to the left, and the surface is fully protonated. The isoelectric point for silica, where there is no net charge, is at about pH 3. The silanol groups are very hydrophilic, and they will interact with other species that are capable of hydrogen bonding, such as water. Water is present in molecular form on the surface through the hydrogen bonding interaction, and this is referred to as physically bonded water. Physically bonded water can be removed by application of relatively low temperature heat once the sol is dried. Adjacent silanol groups can also undergo a reaction that produces water as a byproduct, with the result being additional siloxane bonds. This type of water is referred to as chemically bonded water. It is more difficult to remove than physically bonded water, and so this condensation reaction occurs at higher temperatures than removal of the physically bonded water. This silanol condensation reaction is a key functionality in binder applications. Silica is a very unique colloid, however, and some of the properties are not consistent with the simple DVLO model. One issue with the simple chemical model is that there is not good agreement in the literature on the value for the equilibrium constant for the deprotonation reaction. Thus, reported values for pKa, the negative logarithm of the equilibrium constant, range from 3.5 to 7.9. And as might be expected, these values depend on the ionic nature of the solution phase. Another deviation from the simple electrostatic model is that at high pH, the particles can develop a negative charge that is far in excess of that predicted by the surface ionization reaction. This behavior is rationalized by using a model that the outermost nanometer of the silica surface consists of a somewhat porous, gel-like layer. Thus, the particles in the sol are not hard spheres, but they have a soft outer surface. Finally, a very striking deviation from the electrostatic model occurs at low pH, at or near the isoelectric point of pH 3. Normally, colloids flocculate at the isoelectric pH because electrostatic repulsive forces are minimal. However, colloidal silica has unusual stability at this pH that is not predicted by the theory. This behavior is explained by the introduction of a third term into the total energy expression for the system that is based on strong hydration of the surface with water. The strongly bonded water provides an additional barrier that must be overcome for the particles to aggregate. The previous concepts can now be used as a basis to understand the different Ludox colloidal silica grades. The most common grades are based on an unmodified silica surface, and thus the surface charge depends on pH. Measurement of the zeta potential as a function of pH for these standard grades is shown in the curve on the right. These data were obtained using the electroacoustic method for particle size and zeta potential measurement. At pH above about 8, the charge at the double layer is negative and of high magnitude. Thus, the particles have optimal stability. For pH lower than 8, the zeta potential decreases, and thus the particles become less stable. The pH range of the particles as supplied depends on the particle size and is higher for smaller particles, since those require a higher concentration of alkali for stability. The cations that are commonly encountered in the alkaline Ludox grades are sodium and ammonium ions, although potassium ions can be provided for custom grades. An interesting modification of colloidal silica involves isomorphic substitution of aluminum for silica in the network under high pH conditions where the aluminum is in tetrahedral form, like the silicon. This substitution has an interesting impact on the particle charge. Since aluminum is trivalent and silicon is tetravalent, isomorphic substitution of aluminum into the tetrahedral silicon network creates a charge imbalance of one negative charge per aluminum atom. As a result of this substitution, the charge on the particle is now fixed to the extent that the aluminum is bonded to the network. Thus, as shown in the graph, the zeta potential is no longer strongly dependent on pH. The charge remains negative all the way down to pH 3.5. The reason that the charge starts to decrease at even lower pH is that the aluminum begins to dissolve. Ludox colloidal silicas that have aluminum substituted on the surface are stabilized by either sodium ions or protons. Stabilization with protons is possible, of course, because the fixed negative charge on the particles persists at pH below 7. Another type of Ludox colloidal silica is prepared by modifying the surface with a cationic form of aluminum instead of the anionic aluminate ion as described previously. Shown in the graphic is a representation of a polynuclear cationic aluminum cluster that is stable at low pH in aluminum chloride solutions. The aluminum-based cation is ion exchanged onto the negatively charged silica surface, so that the zeta potential becomes positive rather than negative, as shown in the curve. The shape of the zeta potential curve is qualitatively the same as for pure alumina, which has an isoelectric point around pH 9. These cationic grades are stable at pH between about 3.5 and 6.5. At pH lower than about 3.5, protons can displace the cationic aluminum, which is ultimately detrimental for stability. We'd like to focus now on a few selected applications and highlight the silica functionalities that are important for imparting unique performance in these systems. As a first example, we will consider silica in combination with other inorganic oxides in binder applications. As mentioned previously, one of the first patents for Ludox colloidal silica was as a binder for catalyst particles. Shown in the image is a cutaway of an emission control device used in automotive applications, where colloidal silica is used as a binder. Other prominent industrial applications include precision investment casting, for example, to form the airfoils in jet engines, and in refractory fibers. We will also highlight the impact that colloidal silica can have when incorporated into systems that contain organic macromolecules. In one case, we will explore the impact that the nanoparticles have on a polymer system in the solid phase, as this chemistry is very relevant for modern coatings applications. Finally, we will highlight the unique features that the nanoparticles can impart in a hydrogel system in the fluid phase. This chemistry is relevant for some newer applications, such as in fire retardant systems. The image shown demonstrates how effective these systems can be by the relative burn areas of untreated and treated mowed grass. Investment casting is a process that was developed initially thousands of years ago. The basic process involves forming a mold using an expendable material such as wax, creating a hard ceramic shell around the mold, and then removing the mold. The form, or cast, left is then hardened to the point that molten metal can be poured into it and cooled. Finally, the cast is broken away, leaving the solidified metal form. The images shown depict one of the earliest examples of a casting from the early Bronze Age, from more than 4,000 years ago. The life-size casting was done with copper alloy and contains intricate details. The first patent describing the use of colloidal silica in refractory molds for investment casting dates back to 1945. It was found that the colloidal silica improved the strength of the ceramic cast. Today, investment cast metal parts with complex geometries are used in a wide range of industries, from aerospace to automotive parts, industrial turbines, medical implants, and of course to art forms. There are two main components of a shell system, the refractory material and the binder. Examples of typical refractories are alumina, aluminosilicate, fused silica, zirconium silicate, and zirconia, and these are provided as micron-sized or larger particle-sized powders. In addition to the colloidal silica binder, other minor components can be added, such as polymers and surfactants, to aid in green strength and in the wetting of the wax substrate. The actual amount of colloidal silica in the system that results in ceramic casts of maximum strength depends on the particle size of the colloidal and can represent up to 20% by weight of the system. The workflow for preparing the ceramic cast and ultimately the metal part is shown here. Many steps are involved, and up to about 8 layers of ceramic precursor are applied to the wax pattern. After drying, the shell has to have suitable green strength, and then after firing at high temperature, it must have enough strength and dimensional stability to withstand the addition of molten metal. After the system is cooled, the shell is broken away and the metal part recovered and finished. An important attribute of the slurry is that it must have low and controlled viscosity. Attributes of the ceramic shell are that it must be unreactive with the molten metal, it must have a high melting point, much higher than the molten metal, and the thermal expansion must be minimal or at least predictable. Colloidal silica is advantageous in this regard because the sols are provided as high solids, low viscosity dispersions. Amorphous silica is relatively chemically inert, and once the system has been consolidated, it has low coefficient of thermal expansion at high temperature. There are several physical and chemical processes that are involved with shell formation. First, the shell must be drained of excess slurry and then partially dried. This occurs via evaporation of liquid at the shell surface after a capillary network has formed between the refractory and binder particles. This capillary network is formed when the liquid phase transforms to an elastic gel state via hydrogen bonds between the hydrous oxide surfaces. The formation of the gel state depends on both the concentration of the colloidal silica as well as the particle size. After drying, the shell is then heated at elevated temperature, and this drives off chemically bonded water by condensation of surface hydroxyl groups. Finally, at even higher temperatures, the small colloidal silica particles sinter to form relatively dense regions between the refractory grains. One of the key parameters that is used as a measure of the binder performance is the strength of the shell, as indicated by the modulus of rupture. The MOR is calculated from the applied force at rupture of the ceramic body while taking into consideration the geometry of the part. Ideal performance for the shell MOR, as well as more typical performance, is represented in the graph. Ideally, the green and fired strengths should be very high, while the shells should be easily fractured and removed after the metal is poured into the cast. Typically, it is difficult to achieve high green strength, but optimum strength after the ceramic is consolidated can be achieved by optimization of the binder and refractory system. R.L. Rusher in the DuPont laboratories studied the optimization of the refractory and binder system in detail. He found that there was typically an optimum concentration of the binder at which the modulus of rupture was maximal. With too low of binder concentration, the ceramic showed cohesive failure from poorly bonded refractory grains, while with too high binder concentration, the ceramic showed cohesive failure from the brittle silica phase. The optimum represents the concentration ratio where adhesive forces between the binder and refractory in the interfacial area are maximum. What Rusher found was that the important parameters were the total binder surface area in relation to the total refractory surface area. Each of these is calculated as the mass fraction of the component multiplied by the specific surface area of that component. Further, Rusher experimentally identified the ratio of these areas at the optimum strength for a variety of systems, and then found that there was a linear empirical relation between the areal ratio at maximum strength and the refractory surface area. This expression can be used as a starting point to estimate the binder concentration for maximum ceramic strength for any given ceramic in other applications as well, given the surface areas of the binder particles and refractory material. I'd like to provide a little more detail about the transformation of the colloidal silica during the heating required to harden the ceramic. Shown in the left graph are results from thermal and calorimetric analyses of a dried colloidal silica. The mass loss is represented by the lower curve, and the heat flow is represented by the upper curve. The shaded area above the straight line indicates an endothermic reaction, and the shaded area below the line indicates an exothermic reaction. The starting colloidal silica was one that had been dried at just above 100 degrees Celsius for several hours. The mass loss at temperatures up to about 200 degrees Celsius is from the loss of fizzy-sorbed water, and this evaporation requires a net input of heat. Chemically bonded water begins to evolve at higher temperatures, and this involves condensation of surface silanols to produce siloxane bonds. This process continues until about 800 degrees Celsius and also requires the input of heat. At temperatures above about 900 Celsius, an exotherm is noted, and this corresponds to the crystallization of the amorphous silica to crystalline phases such as cristobalite. Shown in the right graph is additional detail for the specific reactions that occur at corresponding temperatures. The dried but fully hydrated silica surface contains about 5 silanol groups per square nanometer. Initial silanol condensation begins at temperatures above about 200 Celsius and continues to higher temperatures. However, these reactions are mostly from intraparticle silanols, and so there is minimal loss in particle surface area. At temperatures higher than about 600 degrees Celsius, Silanol condensation occurs between particles, leading to a net loss in surface area. Thus, in order to fully sinter and densify the body, temperatures well in excess of about 600 Celsius are needed. Isolated silanol groups are the last to condense at high temperatures. We'd like to turn now to applications that involve mixtures of colloidal silica with organic macromolecules. These materials can be termed nanocomposites, since at least the colloidal silica is of nanoscale dimensions. The motivation for nanocomposites is that in principle, it is possible to combine the advantages of both systems, such as hardness and thermal stability from the silica and flexibility and processability from the organic phase. The small size of the colloidal particles creates a large interfacial area even at low particle loadings, and the properties of the interfacial area can be unique and can confer on the whole system very useful advantages. One commercial driver for nanocomposites comes from the coatings industry, where there is a trend away from solvent-based formulations to water-based formulations to minimize volatile organic compounds. In solvent-based formulations, high glass transition temperature polymers with high hardness can be used because the solvent or co-solvents aid in the resin coalescence during drying. Typically, in water-based systems, resins of lower glass transition temperature, which are generally softer, are used to facilitate cure. But these coatings can sometimes have poor mechanical properties such as scratch resistance. Hybrid nanocomposite systems, if designed correctly, can offer good resin cure and film formation along with improved mechanical properties for the films. One interesting point is the strong, relatively recent interest in nanocomposites as reflected in the open scientific literature and in patent applications. A recent search of the scientific literature using a combination of the terms Ludox and nanocomposite returned over 21,000 hits. There has also been a strong increase in industrial interest since the late 1990s, as shown in the graph. This graph is based on a patent search that involved the combination of the terms colloidal silica and nanocomposite. A total of over 1,700 patent applications have been filed since 1985 involving this topic. The first application we will highlight involves incorporation of colloidal silica into a linear thermoplastic polyurethane system. These polymers typically have high elasticity, high tensile strength, and excellent abrasion resistance. We chose this system because it was a relatively recent study wherein the mixtures were both very well characterized and demonstrated strong improvement in selected functional properties for the mixed system. The characterization of the mixtures included the microstructure as revealed by scanning electron and atomic force microscopies, mechanical properties of the films by both static and dynamic mechanical analyses, thermal stability by thermogravimetry, and water uptake. Polyurethane aqueous dispersions are prepared using hexamethylene diisocyanate with polycarbonate diol and butane diol segments, and with an ionic carboxylate also incorporated into the polymer backbone for dispersion in water. These were then blended in simple aqueous mixtures with varying amounts of Ludox colloidal silica of two different types. Ludox AS40 is an untreated silica sol provided at high pH with ammonium solution cations, while Ludox TMA is an aluminate modified silica sol provided at low pH with protons as the solution cations. Films were cast onto Teflon plates and then dried for 5 days at ambient temperature and then for 20 hours at 50 degrees Celsius. The polyurethane matrix represents the continuous phase, since even at the highest silica mass loading, 50 weight percent, the volume fraction of silica is only about 36%. The authors found that the cast films were all thermoplastic and that the polyurethane dispersion was recoverable after dissolution in organic solvents, followed by addition of water. This indicated that the primary mechanism of interaction between the silica and polymer was via hydrogen bonds and not covalent bonds. The mechanical properties of the film varied with both the type of the colloidal silica as well as the loading. At low loadings, the films were elastomeric. At intermediate loadings, they were plastic. And at the highest loadings, they were brittle. The graph on the upper right summarizes the results of tensile property analyses. The solid curves connect data points for Young's modulus as a function of the silica loading. Young's modulus measures the stiffness of a body, that is, the response in dimension under compression or tension. A large Young's modulus indicates that there is little deformation even when large forces are applied. The films with incorporated colloidal silica demonstrated higher Young's modulus than the film with no silica, and an increase of over an order of magnitude was measured for the highest loadings. The dash curves connect data points for the percentage of elongation at the point of film breakage. For the 5% loading, the elongation at break increased for both the silicas. However, at the highest loading, the films became quite brittle and the elongation at break was reduced substantially. Interestingly, for the intermediate loading, there was a divergence in elongation behavior, with the AS40 showing good retention of elastic behavior. Examination of the microstructure of this sample revealed that the polyurethane fibrils remained intact and the colloidal silica was well dispersed throughout the matrix. The schematic on the lower right shows the results of water uptake measurements. At the lowest loading, the films with colloidal silica showed lower water uptake, decreasing from 5.6% for the unloaded film to 1% or less for the loaded film, in spite of the fact that silica is a very hydrophilic material. At higher loadings, the water uptake increased substantially to over 14%, and this is believed to be from porosity in the films. Since the volume fraction of the silica particles at this loading, roughly 36%, is below the critical pigment volume concentration, the presence of porosity indicates that either incomplete formation of the polymer around the silica's particles occurred, or there's microscopic phase separation. These results demonstrate that the incorporation of the colloidal silica into the polymer matrix substantially modified some of the matrix properties, potentially in useful ways. The last application that we would like to highlight involves the use of colloidal silica to modify the properties of a hydrogel that is normally fluid at ambient temperatures. In this case, the hydrogel is a carrier for an environmentally friendly and long-lasting fire prevention material. This development was recognized as the best venture for the year 2020 by the National Renewable Energy Laboratory in the US. The organic macromolecules that are used to form these hydrogels involve an optimized mixture of hydroxyethylcellulose and methylcellulose. A colloidal silica is incorporated into the hydrogel matrix and confers special properties in the mixture. Many mixtures of the cellulose and silica were evaluated in order to develop optimized formulations, and the hydrogels were evaluated for various properties, including viscoelastic and wetting behaviors. A matrix of high and low molecular weight celluloses were screened, along with a few different colloidal silicas. The ideal formulations showed good wetting performance on vegetation. That is, once applied to the substrate, the wetting coefficients were greater than 1, so that the droplets spread and formed continuous films. Of course, the surface tension of the hydrogel is largely determined by the specific mixture of organic macromolecules. The viscoelastic properties of the hydrogels were explored in detail by the authors using steady shear and oscillatory measurements. Not surprisingly, the various mixtures showed a wide range in properties and were strongly impacted by the colloidal silica. The hydrogel mixtures were shear thinning from somewhat high viscosity at low shear to low viscosity at high shear, which is useful behavior that enables the fluids to be easily pumped and sprayed. Furthermore, for optimum coverage, the viscosity must remain low for a long period of time so that the liquids can spread once they hit the target vegetation. In order for the liquids to be retained on the vegetation, it is desirable for the viscosity to increase in a time-dependent manner, and this aspect of the rheology was also found to be controllable within a useful range. In the graph on the lower right are shown results from oscillatory measurements of the rheology of an optimized hydrogel at ambient temperature and low frequency. This mixture is comprised of 1.2% hydroxyethyl cellulose, 0.3% methyl cellulose, and 7.5% colloidal silica, with the balance water. The black bar represents the storage modulus of the hydrogel, which is analogous to the Young's modulus of a solid in tensile testing. The higher the value, the stiffer the liquid. The value shown indicates that the hydrogel is relatively stiff, roughly comparable to a pudding with high starch content. Thus, as we saw in the previous application, where the colloidal silica caused a dramatic increase in the Young's modulus for a polyurethane polymer, here the mixed silica cellulose hydrogel system is also relatively stiff. The red bar shows data for the loss factor for the mixture at low angular frequency. Tangent delta is equal to the ratio of the loss modulus to the storage modulus of the fluid. Values less than 1 imply elastic, solid-like behavior, while values greater than 1 imply plastic, liquid-like behavior. It is believed that the low values of tangent delta at low frequencies in these optimized samples is related to the ability of the hydrogels to stick to the substrate once it hits it. Finally, once the hydrogel dries on the substrate, it forms a tough film that is not easily washed away with rainwater. All of these properties of the mixed system are considered to arise from strong and dynamic hydrogen bonding interactions between the various components and the silica surface. After optimization of the above properties and extensive field testing, this hydrogel system as a carrier for fire retardants is showing excellent utility in full-scale applications. In summary, Ludox colloidal silicas have fostered industrial innovation over the last 70 years, and new applications are being discovered even today. The closely controlled particle properties are of utility in a great number of industrial applications, and the three highlighted today are in investment casting, thermoplastic polyurethanes, and aqueous hydrogel carriers. The key functionalities in these applications include electrostatic interactions for sol stability, surface interactions via hydrogen bonding, condensation reactions to form covalent siloxane bonds, and sintering and consolidation at high temperatures. The specific interfacial structures that lead to optimized properties in these and similar systems are still of active research interest today. For additional resources, such as emerging studies focused on new applications using Ludox colloidal silica, please visit the grace.com blog. You can also download our newest ebook, An Indomitable Particle. Colloidal silica takes on extreme environments, which explores the versatility of colloidal silica, from stabilizing the ground under buildings during earthquakes, preserving ancient carvings, to keeping lenses and sensors aboard space vehicles clear and clean. You can also follow the Ludox colloidal silica page on LinkedIn to stay up to date on emerging trends, news, and events. We'd like to thank you for your time and attention for today's seminar.
Okay, well, that's the end of the video presentation, and I can see Ali's just about to join us. I think it just disappeared again a second, but yeah, so now that we come to the live Q&A session, and thank you for all of you who've got your questions coming in. We've got a few in there now. We've had a few questions from people that I know, Ali, you've already answered a couple about sort of specific grades of Ludox silica, but what would you say are the main considerations when you're deciding what grade or what type of silica to choose for a particular application?
Great question. So really, there's a variety, as Dave talked about, particle sizes and different ranges of properties, such as the charge of the particles. So the choice of the grade will really depend on the application. The first question to ask yourself is, what is the particle size of the colloidal silica that would really be suitable for this application? As you saw, we have a range of small particle sizes, 5 nanometers, 10 nanometers, up to 15. That would be the range where particles, those kind of particles are very useful as binders. Whereas in the larger particles, such as above 20 nanometers, perhaps those colloidal silicas are more useful for surface modification. So it really depends on the application. Another important consideration for particle size is whether you're looking for monomodal particles or polymodal, and that will really depend on, say, if you imagine with polymodal, multiple different particle sizes in the same colloidal silica, you can imagine the small particles filling in the gaps between the large particles. So that would be perhaps something to consider if you're trying to make a very dense film of silica. Another very important property is the pH range that you expect the colloidal silica will be experiencing in your system. So we have this, most of the colloidal silicas are stable at a high pH, alkaline, but we also have some grades that are stable at the low pH range. And finally, the charge of the particles. If you want a particle to be attracted to negatively charged surfaces, then you would choose a cationic particle. So those are I'd say the particle size ranges, the pH that you expect, and again, the charge on the surfaces.
Great, that's a really comprehensive answer. Thank you, Ali. So we've got a question in from Snea who says, what are the sort of alternatives to colloidal silica, and what are the advantages that silica has over those kind of alternative materials?
Well, for most of the applications that we've discussed, really, there are no good alternatives to colloidal silica. Silica itself is a unique material, whether it's in colloidal form or in solid form. So the properties of the colloidal silica partly come from the properties of silica itself. Firstly, it's a very safe to handle material. Silica itself is this silica that we're speaking about is completely amorphous, and it's in water, so using an aqueous system is always beneficial. And then also it's commercially available. It's a substance that has been made for many, many years, and we know which technologies it can go into, and we're also constantly discovering new technologies that this material can be used for. So as far as I am aware, there is really no alternative. Now you can say, well, do we need to make colloidal silica in the same way? Can we have large particles of silica that are milled down? But there is really no way of making colloidal silica in the same form that it's made unless you use this methodology.
Okay, great. Thanks very much. We've got a question from Natari, which is, what's the difference between the silica in its colloidal form and once it's precipitated?
So the methods of manufacturing those two, precipitated silica versus colloidal silica, are quite different. But at the end, they are in the bulk form inside the particle. They are both amorphous they are both amorphous silica. So the material itself is the same, but it's really the morphology. Precipitated silica is actually a solid material. It is sold in a wide range of particles, mostly in the micron range, whereas colloidal silica is an aqueous dispersion of essentially nanoparticles discretely dispersed in water. And they are stabilized, as Dave mentioned, by electrostatic charge. So they are not a precipitated product, they are a dispersed solution.
Okay, and maybe linking into that, we had a question from Canan, which is a little bit about the stability of particles when they're in water. What are the factors that that affect the stability of dispersions of silica?
Right, so Dave mentioned the pH is a very important factor. As you change the pH, you're actually changing the charge on the surface, and so you're able to change the pH up to a certain point, but there are certain regions where colloidal silica is just unstable unless you do a surface modification and use a different grade. as Dave mentioned. And another very important consideration is the presence of any of high ionic strength, and in particular any multivalent ions in solution. So if you have a high concentration of, say, calcium 2+ or a lot of sodium chloride in your system, then there's always the risk that you're going to completely destroy that electrostatic repulsion, and that your particles with that will aggregate. Now, sometimes you might actually want to do that depending on your application in a certain step in your process. But in general, when you're just storing it or just starting to work with it, trying to dissolve it into your system, it is important to consider pH and the ionic strength of the system.
Great. Well, I think I can see we've got loads of really good questions coming in now. I will just say that we've got time for about 5 more minutes, and if we do get to the point, if we don't manage to answer all of the questions during this session, then Ali and Dave have both said that they will follow up. They'll be able to follow up with you afterwards by email for some of the questions that we don't quite get to. So Ali, you mentioned surface modification at the start of that answer just now. Can you give us a bit more of an idea of the ways that you can modify the surface of the silica to give it different functionality with different functional groups?
Sure. So of course, Dave mentioned that we can treat colloidal silica with alumina. The alumina modification can either change the stability in different pH ranges or change the charge stability. But another very important field that's growing rapidly is the modification of the particles to actually add a organic moieties on the surface. So you can there's a lot of very neat chemistry involving silane reactions with the silanol surface of the colloidal silica. And you can imagine that you can add all sorts of organic functionalities. You can add hydrophilic polymers, carboxylates, sulfonates, amines, all sorts of additional functionalities can be added, and those are in development.
Great. So we've had a question from Yasutaka, who asks about colloidal silica being applied in battery materials. We know that batteries are a massive area, and some of the material challenges in there are very, very difficult. So do you know of any applications and what sort of parts of the battery might be where colloidal silica would be applied?
Yes, absolutely. We know that there are patents out there for using colloidal silica, particularly functionalized colloidal silica, in the electrolytes of batteries, because as Dave mentioned, the silica itself adds some robustness to the system. It adds that stability because it's a ceramic material, but it's because of the particle size you're able to incorporate it in all sorts of matrices. So there's a lot of patents out there on the electrolyte, even in the cathode and the anode, depending on the design. Yep.
Great. And so most of what we've talked about has been very inorganic in nature so far. We had a question from Swaraj who says, do you know of any applications of Ludox silica in medicinal or pharmaceutical ingredients as a binder in sort of medicinal gels? You talked about other kinds of gels. So can you apply it in that direction as well, or not?
There's increasingly research looking into using colloidal silica as to form actually capsules to encapsulate drug delivery. This is a very new application that's being developed by mostly in the academic field, but it is a very interesting topic, and really it highlights how this historic material that's been manufactured for decades now is still finding new applications, very advanced applications beyond the very important industrial applications that Dave talked about.
Yes, I mean, you mentioned the history. I just twigged just at the start of Dave's presentation. I hadn't noticed before, but the Thomas Graham that he's talking about is the same Thomas Graham that our main building, the Royal Society of Chemistry, Thomas Graham House, is named after. So it's as you say, a storied history, but still finding new applications. I think we've got time for maybe one more question, which we've got quite a few questions about controlling the process of making these things to perhaps control the different properties or size distribution. Can you give us a little bit of a quick rundown of the things that you can do to control the particularly size distribution, but maybe some of the other properties as well as you go?
Right. So the nature of it really depends on the method in which you grow your particles. How Ludox is very unique because we're able to make the particle size distribution very narrow, but we're also able to broaden that particle size distribution. So we're able to nucleate very quickly a very small distribution of particles and then grow them to whichever particle size by adding more sodium silicate. And really there are many inputs into the reactor, such as temperature and pH, that we use to control that nucleation and growth step. But we're also able to, as Dave mentioned, make distributions of polydisperse or polymodal grades by causing multiple nucleation events and actually forming a wide distribution. And then we can also broaden the modes themselves. So we have different ways by tuning the reactor properties and the reactor conditions to give us different particle size distributions.
Great. Okay, well, I think we should probably draw the Q&A to a close there. There's a couple of links that have just gone out through the chat function, so do grab those before the webinar ends. And all that remains now is for me to say thank you very much to Ali for stepping in to run the question and answer, and to Dave for giving us a really comprehensive presentation about colloidal silica and some really exciting applications of what we might see this material doing now and in the future. Thanks very much to WR Grace for sponsoring the webinar. As I say, we've got a few URLs and things that have gone out, so do grab those. Thank you, the audience, for coming along to today's webinar. It's been great to have you, and you will get an email with a link to the recording of the webinar within a couple of days' time, and you'll all get a certificate for attending live as well. If you liked this webinar, then do check out chemistryworld.com/webinars to see what other topics we've got coming up, and I hope to see you in another Chemistry World webinar very soon. Thanks very much. I've been Philip Broadwith, Chemistry World's business editor.